Welcome to my presentation. If you want better empirical research, value your theory. In here I want to present my position that what we need in order to improve empirical software engineering research is not just better methods on an empirical side, but also stronger theoretical foundations for the empirical work itself. Why did I write this paper? It's actually a topic that I'm concerned with now for 25 years, because for 25 years I'm working in empirical software engineering, and I always had a focus also from a practical side that we, back when I worked at Fraunhofer especially, we tried to transfer methods and technologies to organizations, and you never transfer some knowledge one-to-one because each organization is different. So you are invariably concerned with the question, how do I adapt something? And if I adapt it, what will be the result of it? And as soon as you try to do that, you realize all results are pretty narrow in the sense that they really talk mostly about specific cases, and the question how to adapt things to a new situation and what the impact might be is not fully addressed. A second motivation is coming from a more philosophical point of view. I'm very much interested in the foundations of science, and if I wanted to compare software engineering also with how other disciplines work. And in that area, often physics, for which I also have some background, is taken as a reference because of its huge success. That's not saying we should do things like people in physics do it, because that is really a different field. But nevertheless, some of the ideas from there and some of the behaviors and ways of doing research might also be useful in a different context like this. My goal is not to give you everything what is written in the paper. It's impossible. I have there 12 propositions. That would be less than a proposition per minute. That doesn't make sense. So my goal is actually to motivate you to read the 6 pages. It's not more, and hopefully give you along the way a few interesting ideas. I suppose most or all of you know this kind of picture or a variant of that, because you find that in pretty many papers on software engineering as well. The idea is we have a theory, we make a theoretical prediction which gives us some hypothesis, we use that as a basis to do empirically some research by empirical inquiry of the real world. We come back with a falsification or support of the result, and then we feed that back into our theory to improve and learn. So there are various ways to present that, but I think that as a fundamental cycle of software of science is agreed in software engineering as well as outside. But if I look at most work on how to improve empirical work, it's actually focusing mostly on the upper part, not so much on the whole cycle from theory through empirical work back, and what this implies for empirical work. And that's what I want to do in this paper. So the purpose of any scientific theory is to allow to make predictions, qualitatively, quantitative, for new situations, and actually along the way to explain them. So what that means is a theory needs to establish strong and standardized concepts to describe these situations. And it does not only need to describe this for the specific empirical study, but in order to be applied also in new situations, it needs to describe it for the larger domain to which something should be applied. This has also the consequence that any theory comes with a defined range of applicability. There are clear preconditions, boundaries, and they should be stated. They should be stated by relating the empirical work to the theoretical foundation. That would also avoid to the external validity fallacy, which is saying, well, my work has a significant external validity, and therefore it applies to every and each software organization in the world, which is of course nonsense. This is not a valid way of arguing. There are further consequences if you look at this relationship of empiricism and theoretical foundation. Empirical work should always clarify the input and output relative to the underlying theories. It should be based within a theoretical framework, and it should not be just standing alone by itself. Like, I come up with a hypothesis, I make an experiment on that, or a case study, or whatever, and then I describe it. This is what I call a theoretical singleton. It stands isolated from the rest of the world, and I would actually argue it's mostly useless for exactly this reason. So in the paper you will find a short study I did where I simply checked the method papers from last year's ESA, and according to my counting, basically nearly no paper was more than just such a singleton, with very few exceptions. So one paper, for example, really nicely presented its underlying theory. Unfortunately, the underlying theory was not a software engineering theory, it just was a psychological theory. So I think we are, as a discipline, very strongly lacking in that regard. Also, for any theory, we should define some sort of operation on the theory, basically describe how to make predictions, how do we combine statements in this theory to derive something new. In Germany, or in German, that's called a calcul, in English calculus. That's not meaning it should be analysis, which is one specific mathematical method, unfortunately with the same name. Also, if you want to combine different individual studies, if you look at other disciplines, especially the classical engineering disciplines, physics and so on, they are using certain types of mathematics to do that, along with laws that they derived. So in order to combine multiple pieces of evidence, what you need is exactly such a calculus. Also, if you want to reconcile new evidence with existing information, meaning to adapt and revamp your theory, you also need such a calculus. It is also central to identify what I call hidden concepts. What's a hidden concept? It's opposed to the basic concepts. It's a concept that is not visible directly in the environment, but nevertheless plays a crucial role for our whole understanding and theory building. If you think about something like physics, energy is such a hidden concept. Nobody has ever seen energy, but nevertheless it's a very fundamental concept, and only by understanding that many advances in the science were possible, and conservation of energy is really one of the very fundamental things. And that's something we see over and over in other disciplines. These hidden concepts play a role, and in order to derive them, we need to understand how do we actually operate on statements in our theory. So that was just a short run-through. In the paper you find a dozen propositions. Unfortunately, I'm not able to give all of them to you, so that's what I could do. And so I hope you feel now a bit motivated to read the full paper. It's just 6 pages, and of course I'm very interested in discussing with you about all these statements. Thank you very much.